Alrighty, so here is the answer key to the second practice quiz we did just on a review day last time. So let's go ahead and work through it. So we'll start here, number one, acid-base neutralization, right? The neutralization reaction always yields a salt and water every single time, okay? When that acid donates its hydrogen, it ends up combining with the OH of the base, forming H2O. And then whatever the anion was from the acid combines with the cation from the base, forming that salt. So sodium sulfite is a salt formed by what reaction? Which acid and base could give us sodium sulfite? So we need a base that has sodium, so it could be this one or this one, and we need an acid that has sulfite. So that one does not, but this one does. So this must be the combination that would give us sodium sulfite as the salt, okay? All right, 6.2 moles of acid is dissolved in water, and the final volume is 2.5 liters. What is the molarity? This is just a straightforward molarity calculation. So you take your moles and divide by your volume. So 6.2 moles of acid, right, divide by the total volume, 2.5 liters, and that gets us 2.48 moles per liter. And I think we need to round. Yep, we do for sig fig, so we're going to go with 2.5 molar acid. We don't know what it is, so I'll just do that. Okay. If we have a solution with a pH greater than 7, that would be basic. Remember, low pHs are acidic and high pHs are acidic. 7 itself would be considered neutral. To calculate pH, we use the equation pH equals negative log of the hydrogen ion concentration. So we see we are given our hydrogen ion concentration. So I'm just gonna plug that in, and it is 0.01. So run that through my calculator, and I get a pH of 2. Alrighty. Moving forward, here is a little mini titration problem, okay? So we know that we have a base, and that base, we have a volume and a molarity. Remember, this molarity right here, this is simply moles per liter. So if we can combine that volume with that molarity, we could get number of moles. Our acid, we just have a volume, right? We don't know its concentration, so we don't know how much of it there was. This problem steps it out for you in a bunch of little baby steps as opposed to making you just solve the whole thing. So let the easy problems be easy, right? How many moles of base were used? Well, we know the volume and we know the concentration. That's all we need to know how many moles were used. So I'll start with my volume. I have 365.0 milliliters of my base, which is sodium hydroxide. Milliliters aren't going to work for my molarity, so I'll go ahead and do my metric conversion. I know that there are 1,000 milliliters for every 1 liter. Now I'm in liters. Now I can use my molarity, and I know that my molarity is 2.46 moles of our sodium hydroxide for every 1 liter of that solution. Now I'm in moles, right? I'll double check my units. My milliliters cancel, my liters cancel, and I'm left with moles of NaOH, which is exactly where I want to be. Run the numbers, and I get 0.8979. Considering significant digits, I have 0.898 moles of NaOH. Units and labels on everything, box around my answer, it's perfect. All right, now how many moles of acid were used? So this is where we have to use a balanced equation. So before I go any further, right, if I want to start talking about acid, I know that I only have that volume. That's not going to help me. I have to use the amount of base that I have. The only way I'm allowed to do that is if there's a balanced equation that relates the two. And there is, right? They're doing an acid-base neutralization. So we know we have HCl plus NaOH to yield NaCl and H2O. This is a simple one-to-one. Everything is already balanced. Notice if it wasn't a one-to-one ratio between the acid and the base, we would have to incorporate that in our stoichiometry. So we can start with our answer from over here. So we'll go and say, okay, if I used 0.898 moles of my NaOH, how many moles of the acid does that correspond to? So I need to use my mole ratio. For every 1 mole of HCl, there is 1 mole of NaOH. So 1 mole NaOH relates to 1 mole HCl. Now I'm in moles of acid. That's all I need. Double check that my units cancel. They do. And I get an answer, surprise, surprise, of 0.898 moles of HCl. You do not get to just say, hey, it's 1-to-1, so it's the same. I need to see your thinking. I need to see your work. Okay, so now, excuse me. So now what is the molarity? So now we just have to divide by the volume, and we have that volume up here, right? So we know if we have 0.898 moles HCl in a volume of 136 milliliters, which I'm just going to do my metric conversion in my head, so that's 0.1360 liters. Now I can do my division, and I get an answer of 6.60 molar HCl. All right, so there would be my answer there with my 3 sig figs that I get to keep. Now I want to know the pH. Now we're going to get a funky number here because this is a pretty concentrated solution of HCl, so that pH is going to be real low. So again, to do pH, we need the concentration of hydrogen ion. Now looking at HCl, we see that for every 1 HCl, we have 1 hydrogen ion. So we could say that the ratio is 1 to 1, or we could just do a quick conversion, and I'm going to go ahead and do it that way, right? If I have 6.60 moles per liter of HCl, I can just convert that and say, well, for every 1 mole of HCl, I have 1 mole of hydrogen ion, right? Let's check my units. My moles of HCl cancel, and I'm left with moles of hydrogen ion over liters, and that's exactly where I want to be. Plug those numbers through, and obviously it's 1 to 1, so we don't need to plug anything, sorry, and we get 6.60 moles per liter, or molar, hydrogen ion. That's our concentration, so to do pH, we just have to say, right, pH equals negative log of our hydrogen ion, so that's going to be our 6.60. Plug that into your calculator, and we get a pH of negative 0.820. Now, again, remember we said mathematically, yeah, you might get some little negative numbers, you might get some numbers just barely over 14, and that's okay, right? Conceptually, think of the pH scale as 0 to 14, but in reality, the math can get us some numbers that are a little bit different than that. All right, moving along, number 7. Here we are doing a problem it's just limiting reactant, right? Theoretical yield and limiting reactant. So here we're starting with a volume and a solution and a concentration of one of our compounds and a gram value of the other, okay? So alrighty, so we want to go through and do our theoretical yield calculation for both, and that will let us see which one is our limiting reactant. But before we can do any of this, we need a balanced equation, right? So let's do that first. Let's see, so we have ammonium phosphate, so that's going to be our NH4. Phosphate is a 3-, and ammonium is a 1+, so I'm going to need 3 of these with our PO4, and that's solid, but it's going into a solution. So during the reaction, they're both going to be aqueous. So let's just go ahead and call it aqueous. We're reacting that with magnesium chloride. Magnesium is a 2+, chlorine is a 1-. Therefore, this would be MgCl2, again, aqueous. When they react, they're going to swap partners. If you check your solubility rules, you'll see that magnesium phosphate is not soluble. So we will have our magnesium phosphate, Mg3, PO4 2 is a solid, and sorry, I'm out of space here. We're going to add to that our ammonium chloride, and that's just 1 of each because they're both a +1 and a -1 respectively. What am I at? NH4Cl. So now we need to balance our equation out, and you end up needing 2 of those. Let's see, you need 3 of these magnesium chlorides, you need 6 of these bad boys, the ammonium chlorides, and only 1 of the magnesium phosphate. Oh, and this guy is an aqueous. Okay, so now we have our balanced equation, even if it's a little funky shoved in over there. Alrighty, so now I can do my work, right? Because I can't do theoretical yield calculations unless I know my mole ratios. I don't know my mole ratios unless I have that balanced equation. So now I'll go ahead and do my work. I'll start with the ammonium phosphate. So I know that I have my 3.83 grams of ammonium phosphate. And I'm just going to try to save room here a little bit. Alrighty, so now I need to get to moles. I calculated the molar mass by adding up all of the ammonium ions and the phosphate ion, and I get a total of 146.09 grams for every 1 mole of ammonium phosphate. Now I'm in moles of ammonium phosphate, but I need to convert and get to moles of product. And I want down here, I want the yield of the solid product. So I'm going to go ahead and aim for that solid product. That way I don't have to redo any work. So I know that for every 2 ammonium phosphates, there is 1 magnesium phosphate. Now I'm in moles of magnesium phosphate. I'm going to want, it doesn't say specifically whether I want grams or moles, so I guess technically you could just go to moles. I'm going to go ahead and take it all the way to grams, though, because that's more reasonable for a theoretical yield. So I know that every 1 mole of magnesium phosphate, that has a mass of, what did I get here, 262.87 grams. Now, I used my periodic table, which truncates at 2 significant digits, so our digits here might be slightly off. Double check that your work matches, and then even if your number is off by, a digit or 2, you're still totally good. So now that's it. Let's double check that our units cancel. Grams cancel, moles of ammonium phosphate cancel, moles of magnesium phosphate cancel, and we're left with our grams of magnesium phosphate. Plug it in, and we get 3.45 grams of that magnesium phosphate. Okay, now we'll do it the other way around. So now I'll look and I'll say, okay, my other one is from a solution. It's not from a mass. So I'll start with my volume, and I'm going to go ahead and just do my metric conversion in my head. So I have 0.15050 liters. Now I use my concentration. I know that for every 1 liter, I have 0.855 moles, and this is my magnesium chloride, right, MgCl2. Now I'm in moles, so now I can do my mole conversion. Let's see, it is 3 magnesium chlorides, right? I'm just getting this from the balanced equation for every 1 magnesium phosphate. Now I'm in moles of magnesium phosphate, so I just throw that same molar mass as I used above. Every 1 mole of magnesium phosphate has a mass of 262.87 grams. Again, I'm going to go ahead and double check my units. My liters cancel, my moles cancel of magnesium chloride, up to moles of magnesium phosphate, those cancel, and I'm left with my grams of magnesium phosphate. Plug those numbers in, and I get an answer of 11.28 grams of magnesium phosphate. Now, which one's our limiting reactant? Well, this should be pretty clear, right? Obviously, this one produced less, so that must be our limiting reactant, which makes this guy down here our excess reactant. So we have ammonium phosphate as limiting, producing 3.45 grams of the magnesium phosphate. That is our theoretical yield. Oops, sorry. So I'm going to go ahead and just rewrite that value down here, but I'm not going to redo any of that work because I already did it, and it's right there, and you can see it all, right? I could see it all if I was judging your work, if I looked like this, right? So I'm just going to rewrite it there so the answer's in the right spot, and I'm going to, just kind of say, see, look, I showed you already up there. All right, so that gets us through the front page, right? Not too shabby. All right, let's shift over to the other side. Now we're spending some time looking at conjugate acids and bases. And again, this is where we recognize that an acid is a proton donor or a hydrogen donor, and a base is a hydrogen acceptor. So an acid will give up a hydrogen, becoming a conjugate base. A base will accept a hydrogen, becoming a conjugate acid. So looking here, we have the ammonium ion, NH4+, and on the other side we have NH3. So we know this must be our acid becoming our conjugate base. That makes this OH minus our base. Tack a hydrogen on there, and it becomes our conjugate acid. Okay. Next one down, we have HPO4 2 minus and H2O. Our products are H3O plus and PO4 3 minus. So the HPO4 is the one that's giving up the hydrogen, right? Sometimes you have to look at both sides to be sure which one is doing what. This is our acid, making this our conjugate base. Therefore, this is our base, making this our conjugate acid. Here we go. HCN and SO3 2 minus, or minus 2, whatever. So the second reactant there can't give up a hydrogen, so there's no way that that's our acid, right? So this must be our acid. This must be our base. Therefore, we should have a CN minus, and we do. That's our conjugate base. And we should have an HSO3 minus, and that will be our conjugate acid. Okay. Then we have phosphoric acid and ammonia. Take a hydrogen from phosphoric acid, give it to the ammonia, and you get an NH4 plus. Therefore, that's the one that gained the hydrogen, right? The NH3. So this is our base. This is our acid. Acid becomes the conjugate base. Base becomes the conjugate acid. Okay. So then this next problem is again looking at conjugate acid-base pairs, but really all we're doing here is saying, hey, do you understand what conjugate acids and bases are, right? They are different by a hydrogen. So notice the ClO4 minus, does that have a hydrogen to give? It totally does not, right? So there's not going to be a conjugate base. It can't give up a hydrogen, so it can't behave as an acid. Therefore, it can never become a conjugate base. However, it could absolutely accept a hydrogen, becoming a conjugate acid, which would give us HClO4. Okay, SO4 2-, exact same situation. It has no hydrogen to give, so it could not possibly be an acid. It could not possibly become a conjugate base. However, it could accept a hydrogen, becoming HSO4-. Therefore, it can act as a base, taking that hydrogen, becoming the conjugate acid. HCO3-, here's one. It's like water. It's amphoteric. It can do either or. If it gives up its hydrogen, it becomes a conjugate base. So that would be the CO3 2-, right? If it accepts a hydrogen, it would become the conjugate acid, becoming H2CO3. Okay. HNO3, right? So HNO3 could happily donate that hydrogen, nitric acid. It's going to do that, becoming the conjugate base, NO3-. Now, could it tack on another hydrogen, becoming a conjugate acid? I mean, I guess you could come up with a way where it could. It could become H2NO3+. The reality, however, is that it's not going to do that. But you don't know that, right? So if you're just following the rules of what makes something a conjugate acid or a conjugate base, you could write this and I would totally understand that. I want you to think about, though, if you're, perplexed about why do I know it will or won't. And remember, with water, when we talked about it can act as an acid or a base, it all depends on what it's reacting with. And there just is no acid strong enough to be able to shove another hydrogen on to that nitric acid. The nitric acid is just not going to do this, right? So if you wrote this, fine, but, it's really not going to happen. All right. So moving on to our last problem. So here we have another stoichiometry problem, looking at theoretical yield, limiting reactant, percent yield. So let's just work through it. We know we are going to need a balanced equation. So here we go. We know we have ammonia, NH3, and that is a gas. And we are combining that with copper oxide, which is a solid, to form our nitrogen gas, our copper solid, and our water. Right. Oh, I started adding my balancing here. Sorry. So I had already done my balancing. So let me just throw these numbers in here. We have a 3 in front of a few things, a 2 in front of this, and the nitrogen stays all by itself. So there is our balanced equation. Let me get these last parentheses on here. And there we go. Okay. So, right, notice in the problem, NH3, copper oxide, other products are copper metal, and water. So all the information we need in here, and making nitrogen gas, right? The information was all given in the problem. You just have to sift it out. So again, theoretical yield, start from each starting material and work your way to your theoretical yield. And I want to know about nitrogen, right? So I'm going to be aiming towards nitrogen. Notice it says in liters, and it gives us this collected STP. So this tells me right away we're going to need to use molar volume of a gas. And period 2 people, I am so sorry, I'm a big fat liar. I flipped your conversion. Molar volume of a gas is 22.4 liters per 1 mole. I'm sure whatever you worked out was a super wonky answer if you used it the other way around. So that's your conversion factor. Okay. Alrighty. So we will start at the beginning, and we have our 9.35 grams of ammonia. So 9.35 grams of our NH3. And we'll just cruise forward. I already know I'm going to be doing 3 conversions. First one is molar mass, 42.45 grams for every 1 mole of ammonia. Now I need my mole ratio. For every 2 ammonia, there is 1 nitrogen gas that is yielded. And we know that every 1 mole of nitrogen gas is going to have a volume of 22.4 liters. That's our molar volume of a gas conversion. And then let's knock down our units. Grams of ammonia cancel, moles of ammonia cancel, moles of nitrogen cancel. We're left with liters. That's what we want. And we should get a value of 2.4669, which would become 2.47 liters. That is an L, not a 7. I apologize. 2.47 liters of nitrogen. All right, next one, we will start with our copper oxide. We have 87.5 grams of the copper oxide. Again, I know I'm going to want my 3 conversions. First one's molar mass, 79.55 grams for every 1 mole of copper oxide. Then we need our mole ratio. There are 3 moles of copper oxide to yield 1 mole of nitrogen gas. And then again, just that molar volume of a gas, for every 1 mole of nitrogen, it has a volume of 22.4 liters. Again, let's cancel out our units. Grams of copper oxide cancel, moles of copper oxide, moles of nitrogen, and again, left with liters. And that gets us 8.212, which would be 8.21 liters of N2. Now, it's very clear to see that obviously our theoretical yield is this 2.47 liters, making the ammonia gas our limiting reactant and the copper oxide our excess reactant. Okay, so we know that this over here is our theoretical yield. Okay, so now we want to know how many grams of excess reactant remains, right? So we need to say, okay, how much of this copper oxide did we use? We know how much we had, right? We started up here with the 87.5 grams. We're not going to use it all. So how much did we use? So again, you could start from the amount of product you created or from your other reactant. I'm going to go ahead and start from the other reactant. So let's see here. I'm going to say if I'm using my 9.35 grams of ammonia, how many grams of copper oxide will I use? So again, let's get to moles. So there's my 42.45 grams for every 1 mole of ammonia. Mole ratio, but this time I'm doing the mole ratio between the ammonia and the copper oxide. So for every 2 moles of ammonia, there are 3 moles of copper oxide. Now I'm in moles of copper oxide, but I want to get to grams so I can figure out how much I have left over. So I'll use the molar mass that I already used up above. For every 1 mole of copper oxide, it has a mass of 79.55 grams. Now I'm in grams of copper oxide. Let's double check that my units work out. Grams of ammonia cancel, moles of ammonia cancel, moles of copper oxide cancel, and we're left with our grams of copper oxide right where we want to be. I get an answer of 65.5 grams of copper oxide that we used, right? That's the amount that we used. That's not the answer. We want to know grams of excess reactant that remain, right? That's what we're looking for. So we have to take how much we started with, right? We started with our 87.5 grams of copper oxide. We used our 65.5 grams of copper oxide. Subtract the two, and we get the amount remaining, and it looks like we get a 22.0 grams of copper oxide remaining. Okay, so this is how much we had. This is how much we used. Okay? That gives us our answer right there. All right, so then for percent yield, right? Percent yield, the formula is always the actual yield over the theoretical times 100. That gets you your percent yield. So let's figure it out. How much did we have? So our actual yield, it tells us up in the question, right? It yields, right here, 5.93 liters of nitrogen gas. So we know that we yielded our... Oh, wait a minute. Why is that so wrong? Not wrong. Wait a minute. Hang on a second here. All right, I cannot find where I went wrong, so I don't think I did go wrong. I think that what's weird about this question is this actual yield. I think that is a funky number. So just roll with the math, right? If you see something that looks weird, like I'm looking at this seeing I'm gonna have well over 100% yield. So if you see something funky, just keep going, right? Correct your work, make sure you did it right. But if it's just weird, just do your very best. So I'm looking at this. I'm tired. It's Sunday. I want to get this posted for you guys, so I'm going to post it. And I'm just going to say I really kind of think that this number is wrong because I'm not seeing the error anywhere else. So I'm going to go ahead and just use it, and we're going to have a big weird percent yield. I'm perplexed, to be perfectly honest. 100% perplexed. Okay, so we had our theoretical yield, which was our 2.47 liters. Our actual yield from the question is the 5.93 liters, times that by 100, and for some reason this is different than the other math that I did. I am super perplexed, but that's all right. 2.47, and I would get 168% yield. Clearly that's ridiculous, But again, I can't spot that error and I need to move on with my day. So we're going to leave it at this. And, but to check, right, to make sure that I didn't have like a big egregious error, I'm just going to switch to yellow here to kind of highlight a few things. Like, right, I went through, I'm starting with the right amount of ammonia. That's not wrong. That's the amount that I had there. Molar mass is correct. Mole ratios are correct from my equation. I double checked the balancing of my equation. That's correct. And now we know that this molar volume is correct because I fixed it from before. So this value here is perfectly fine. Other one, same deal. It's fine. It makes more. It's not there's not a different value there. So that's it. It's right. Like those are the numbers that we have. So you just kind of have to go with it. So this is a little weird, but just accept it. And honestly, for you guys, working on that process is more important than any right answer. All right. I hope this helps. Sorry, this last one went weird. I am confused, but that's okay. I don't mind being confused. So that's it. So here we are. No, come back. So here we go. Here's the quiz. Here's the key. Check it out. Be ready for your test tomorrow. Yay. And I will see you then.